Thank you for the introduction and thank you for the invitation to give this lecture today. Actually, the topic is very broad, so I decided to limit the topic to 3 future ESA missions. Possibly they will not be addressed during the later part of the course. So I would like to say something about the future Genesis mission, Moonlight, and the Galileo of the second generation. All of them are, in fact, ESA missions, but they are not directly related to the Earth Observation program, but indirectly the Earth Observation program also uses and will benefit from these missions. Let's introduce myself very briefly in the beginning. I studied at the University of Bern in Switzerland. I graduated with a PhD degree in physics and astronomy at the Astronomical Institute. Then I was a postdoc there. Now I'm working here at the Wrocław University of Environmental and Life Sciences at the Institute of Geodesy and Geoinformatics, and I'm also the member of the ESA Genesis Science Advisory Committee, GSAC committee, since this year. So, as I said, I will address 3 main topics during my presentation. I will start with Genesis, because everything starts with Genesis in principle. Then I will move to Galileo of the first and second generation, and I will also say something about the current status of the Galileo constellation. And I will end up with the Moonlight mission. The Moonlight is actually GPS or Galileo for the moon, but not only, because it will serve not only for the positioning navigation, but also for the communication on the moon. Starting with Genesis. In space geodesy, we use 4 main techniques to observe satellites and also to observe the some extraterrestrial sources. So we use satellite laser ranging. In this technique, we use laser pulses to measure distances to artificial Earth satellites and also the moon. Then we have very long baseline interferometry, VLBI. In this technique, we observe the quasars, which are extragalactic radio sources, and we do it to have the exact orientation of the Earth as a planet in the external reference frame. We use Doris technique. In this technique, the low-orbiting satellite receives the signals from the ground transmitters to have very accurate orbits in short time. For instance, Sentinel-3, A/B, Sentinel-6 use this technique to get the near real-time precise orbits. And finally, we have the global navigation satellite systems, GNSS. We know GPS very well, also the European system, Galileo. Then we have GLONASS, the Russian system, and also Beidou, which is the Chinese system. And to connect all these techniques, we typically have to measure distances on the Earth between the VLBI telescopes, satellite laser ranging telescopes, antennas on the ground, and so on. But instead of measuring it on the Earth, we can also collocate or combine all these techniques on board one satellite. This is why the Genesis 1 was proposed. Now the satellite is scheduled for the 2027 to combine all these techniques on board one satellite. So from the Earth, on the Earth we have 4 techniques. We GNESIS will transmit signals at the same frequencies as the VLBI technique. It will be equipped with the laser retroreflectors for the two-way measurements between the Earth-based telescopes and the satellite. And it will also receive the Doris signals. GNESIS will be orbiting the Earth at the height of about 6,000 kilometers, so it's much below the GNESIS constellation. So it will receive from the top the signals from the GNESIS missions, such as Galileo or GPS. This will be one antenna. The same signals will be tracked on the Earth. But GNESIS will be equipped also in the nadir pointing antenna. This will be the very first time when we will have some signals from the other side of the Earth. Of course, the satellite cannot be directly behind the Earth, because then it will be impossible to receive the signal. But otherwise, the second GNSS receiver from the nadir antenna will also allow us to make the connection between four techniques even stronger. We call it the space tie because four techniques, optical and microwave techniques, will be combined on board one satellite. The funding for this mission was settled last year in November 2022, so we are sure that the mission will be realized. And let's have a look at some simulations for GNESIS. These simulations were prepared at our institute. So starting with the Galileo only solution, when we track on board only the Galileo signals, we can reach the, for instance, clock error accuracies at the level of 0.5 nanoseconds. 0.05 nanoseconds. The same is for the Galileo orbits. The accuracy is at the level of 14 millimeters. But if we add to that just one GNESIS satellite with the zenith antenna, we can reduce these errors by 20%. If we add only nadir antenna, we can further reduce the errors. And finally, if we combine both the zenith and nadir antenna, both the clocks and the orbits of the Galileo constellation can be improved. So we can get the connection between two techniques, four techniques of space geodesy, and also we can improve the quality of the Galileo orbits and clocks. Here we have the observations from GNESIS, from the zenith antenna. So here we have the observations coming from the upper part with respect to the low orbiting GNESIS, and here we have the observations from the other side of the Earth. Of course, we have to exclude the observations from the other side of the Earth and also passing through the atmosphere. So we see that many more observations can be actually provided by the nadir antenna, and this will be the very first time for a low orbiting mission with such kind of the antenna, because the zenith pointing antenna are already installed on many missions like Sentinel-1, 2, 3, 6, and so on, to get the very accurate orbits, final orbits of the low Earth orbiters. Galileo consists of 3 orbital planes, and as I said, a little bit more observations will be collected by the zenith antenna, nadir antenna, but these observations will be a little bit lower quality because the angles are very untypical, and the Galileo constellation was not designed for tracking these signals. Nevertheless, even if this will be a challenge, we hope that the accuracies that we get will be much better with respect to what we have today. So here we have again, for instance, the impact on the semi-major axis. So this is one of the Keplerian parameters that defines the size of the orbit and the inclination angle, so the elevation of the orbital plane with respect to the equator. So this is a situation when we use just the ground measurements, and here this is the situation if we add to the ground measurements the genesis signals from the nadir and zenith pointing antennas. So we can reduce the errors from the level of 14 millimeters to 7 millimeters, so we can come closer to our goal of 1 millimeter reference frames. Let's move now to the Galileo constellation and the relationships between the Galileo and geodesy. Galileo contributes to geodesy in many aspects. This year, ITRF 2020 was released. This is the International Terrestrial Reference Frame, the latest realization that is used for all other purposes like the Earth observations, navigations, positioning, and study of the Earth as a whole planet with the highest possible accuracy. And for the first time, the Galileo constellation was considered in the realization of the terrestrial reference frame. Galileo also provides Earth rotation parameters with even higher accuracy than GPS, because GPS has a deep resonance with the Earth rotation, because every 24 hours we have 2 revolutions of GPS satellites, so we have a deep resonance 2-to-1. So some sub-daily tidal constituents cannot be very well determined using GPS data, but they are much better determined using Galileo, even if Galileo constellation is still not fully operational. Galileo observations can serve also for the fundamental physics. 2 of the Galileo satellites were accidentally launched into eccentric orbits, and because we have very accurate hydrogen masers, so atomic clocks on board Galileo satellites, they can be used to confirm the Einstein's theory of general relativity using the clock gravitational redshift. They could be also used to confirm some effects emerging from general relativity, like the Schwarzschild effect, de Sitter of lens sphering, or they can be also used to determine the post-Newtonian parameters describing the space-time. There are also many applications of Galileo, like determination of station coordinates, tropospheric parameters, the parameters describing the ionosphere, real-time products, precise point positioning, determination of precise low Earth orbiting satellites, orbits, and so on. Galileo also allows us to combine 2 techniques on board the satellites. We heard about 4 techniques, but Galileo satellites were equipped with the laser retroreflectors, which is also different than that in the case of the GPS constellation. So we can combine satellite laser ranging as well as the GNSS microwave observations on board Galileo, which is not possible on GPS because only 2 very early GPS satellites were equipped with these retroreflectors. From Galileo, we have very detailed metadata. They can be used for the construction of the impact of the solar radiation pressure on satellites, and then to determine very precise orbits, and they also include absolute antenna calibrations. For GPS, we have this information only for the very recent satellites, not for the historical satellites. And this is why Galileo was used for the determination of the scale of the latest International Terrestrial Reference Frame realization, ITRF 2020, GPS could not be used for that purpose. GLONASS could not be used, but from Galileo, because we got the antenna calibrations, we could compare the scale of the reference frame between that provided by the VLBI technique, SLR, which is here, and GNSS, which is in fact Galileo, and also here the Galileo is extrapolated back to the past, because the earliest contribution of Galileo started in 2013 when we had the first in-orbit validation satellites launched. Due to the retroreflectors installed on board Galileo, we can validate different analysis centers that determine Galileo or GLONASS orbits, and we can compare and also validate the accuracy of the orbits. If we take, for instance, the ESA orbits for the Galileo fully operational capability, Galileo Fox satellites in eccentric orbits and Galileo IOF orbits, so in orbit validation, we see that the agreement between two techniques on board Galileo is at the level of 1.8 millimeters, 2.1, 0.6 millimeters. So we have a great agreement between satellite laser ranging, so this is an independent technique providing observations directly from the Earth, and the microwave observations provided by the satellites. Looking at the standard deviation, we are now for single observations at the level of 13, 14 millimeters for best orbits, and in this case, one of the best orbits are provided by the ESA Analysis Center. If we study the errors in the Galileo orbits, typically we use a specific geometry. So we study the geometry, relative geometry between the satellites, the Earth, and the Sun. So if Galileo satellites are equipped with large solar panels, and also the body of the bus of the satellites is typically elongated. But we want to have the models that take into account all perturbations acting on the satellites, to take them into account to end up with the as accurate orbits as it is possible. So we study, for instance, the residuals, so differences between microwave-based orbits and the satellite laser ranging, so the independent technique provided by the ground-based laser observatories. So this is what happens if we use just the empirical orbits without any metadata. And for the very low beta angles, so when the Sun is very low above the orbital plane, we see some patterns, especially when the satellites enter the Earth's shadows. But these patterns can be removed to the great extent if we use the empirical and physical orbit model. So if we use the metadata which were released for Galileo but were not released for other systems in such details as for the European navigation system. Nevertheless, for the situation when the Sun is almost perpendicular with respect to the orbital plane, we see still some patterns which can be further removed if we combine two techniques. So the microwave technique on board plus the satellite laser ranging. So if we have two independent observations, we see in principle no further patterns. And we can do exactly the same for different IGS analysis centers, so the analysis centers of the International GNSS Service. We did it for Center for Orbit Determination in Europe, for ESA, and so on. And we see that ESA orbits are again the best for the Galileo satellites. And this is the same for the in-orbit validation orbits, in-orbit validation satellites, Galileo satellites, but we see a small pattern for the high beta angles when the sun is almost perpendicular with respect to the orbital plane, because ESA uses only microwave observations without satellite laser ranging. The combination of two techniques allow us to provide the space-tie, at least between these two techniques, between the GNSS antenna on board Galileo and the laser retroreflector array. So we can reconstruct the local tie, which can be measured also on the Earth between the GNSS receivers and SLR telescopes. And if we do so, this is what we get. This is the red line is the ground measurements. So something what was measured on the ground, and the orange line is the local tie that was calculated based on GNSS and SLR observations. This is the a priori value, which is off both measurements. So we got the long-term agreement at the level between 3 and 4 millimeters between two techniques if we combine the observations on board Galileo satellites, and the strength of the one-day connection between 30 and 50 millimeters. I said in the beginning something about specific signals that are included in the GPS products. Here we have the time series, this periodogram of the time series of the positions derived from GPS, the northeast up component and the zenith total delay. Actually, this is a difference between Galileo minus GPS, GLONASS minus GPS, and multi-GNSS minus GPS. Positive peaks mean that Galileo introduces additional artificial signals to the time series of the positions. Negative peaks mean that Galileo reduces the peaks introduced, or the signals introduced by GPS. So we see that these peaks are much larger below the zero line here for the difference between Galileo and GPS, which means that GPS had these signals which can be reduced by Galileo, which are not found in the Galileo time series, whereas Galileo introduces also some own signals, but they are much smaller than those introduced by GPS, and the same is for the east up component and so on. For the GLONASS case, we see that GLONASS tends to introduce many more signals related to the orbit modeling issues. For the combination of three GNSS constellations, we see that only very small signals can be introduced, but most of the signals that are related to the GPS revolution period, so they are harmonics of the sidereal day, and the harmonics of the sidereal day, so 24 hours or about 12 hours, they can be reduced to the great extent. So we are now waiting for the launch of last 10 satellites, Galileo satellites of the first generation. In parallel, the Galileo of the second generation is already in the preparation stage. The first satellites should be launched in 2026, which are manufactured by Airbus, and in 2025 by Thales Alenia Space. They're going to include upgraded atomic clocks. Already today, Galileo has 4 billion users. And last but not least, there are also plans in ESA for the LEO PNT. This will be a constellation of LEO satellites, a mega constellation in low orbits that will support the positioning, navigation, and timing services in near future using these low orbits of about 600 kilometers. Now I will move to the last topic of today's presentation, the Moonlight program. Moonlight is a program that should provide the positioning, communication, navigation services for the future lunar missions. Recently, we heard about the failure of some missions, like the crash of the Russian mission, of Japanese mission, but the Indian mission managed to land on the moon. ESA is especially interested in the south pole of the moon because the ice water was found there in some craters. So ESA decided to construct a dedicated navigation system for the moon with the main interest in the south pole, where in the future possibly a base will be constructed. So we have these eccentric orbits with the aposelines close to the south pole and periselines close to the north poles of the moon. So the satellites will pass by very quickly above the North Pole, and they will spend most of the time around the South Pole. In the first stage of this mission, only 4 satellites are meant to orbit the moon. In the final stage, the positioning, navigation, and timing services will be provided for the entire surface of the moon. So the initial services are planned after 2027. Before that date, we have the Pathfinder mission that will test, for instance, the capabilities of receiving very faint, very weak signals from the Galileo constellation at the lunar distances. So the Moon GNSS receiver will be installed on the mission in the first stage. For the lunar navigation mission, international consortium were established with the La Sapienza University of Rome in Italy as with the PI of the consortium. We also contributed to that project in terms of providing the broadcast messages and also analyzing the accuracies of the orbits for these lunar orbiters. Now we are in the phase 2 of the mission that should provide the positioning for the South Pole, also the landing services for the future lunar missions. The moon is very interesting from the reference point of view because the moon has a natural meridian 0. The Greenwich on the Earth is not natural. It was established only for the as an agreement. There is no troposphere or ionosphere on the moon. There is no tidal transport because there is no hydrology, oceans, or atmosphere. So, for instance, the lunar rotation can be predicted very well as opposed to the rotation of the Earth, because on the moon we have the interaction between the hydrology, oceans, and the atmosphere. And we know the rotation of the moon, the libration of the moon very well, thanks to the lunar retroreflectors that were installed by the Apollo missions, Apollo 11, 14, 15, and also 2 Russian missions, Soviet missions, Luna 17 and 21. The future retroreflectors will be installed next year. This is the retroreflector that is going to be installed by NASA next year. Actually, for the lunar laser ranging, we use almost the same stations as for the satellite laser ranging. So there's the same observatories that track Earth orbiting satellite. Some of them are capable of measuring distances to the moon. Yeah, I will skip these slides. The gravity field of the moon is very well known thanks to the GRAIN mission. It was a double mission which measured distances between two satellites. But the problem was that the far side of the moon is not mapped as well as the near side of the moon, because every time when the satellites were behind the moon, the contact with the Earth could not be continued. So we have very well mapped the near side of the moon, but the far side we see some features, some spurious features in these areas, because we had to use the extrapolated orbits because there is no navigation system today, but in the future there will be. So our job was to represent the orbit, the quality of the orbit, and the main challenge was the passes through the North Pole in the peri-Selene because of the large gravitational perturbations as well as the high velocities for those passes of satellites. Thank you for your attention.